Molecular orbital theory, looking at electron delocalization in molecules. Now, if you consider the idea of combinations of orbitals, we start with the notion of valence bond theory, which we've discussed before. Valence bond theory is used to show how orbitals form and how molecular geometries arise from those orbitals. They operate looking at the overlap in atomic orbitals. So all atoms have orbitals to them, we know, like s orbitals, p orbitals, and how those orbitals overlap determines the bonding and the geometry of a molecule, according to valence bond theory. Orbitals are either pure orbitals, which we call atomic orbitals, or hybrid orbitals, which are mixtures of atomic orbitals and used for bonding to gain particular configurations. Now, bonding will either consist of a single bond, which is called a sigma bond, and any first overlap between orbitals will form a sigma bond. Subsequent overlap for p orbitals will form a pi bond or a double bond, and then from there a triple bond. Hybridization is the process where we mix orbitals together, which creates an equal number of orbitals with what we call degenerate energies. That means their energies are the same. Now, molecular orbital theory, or MO theory, doesn't look at the overlap of atomic orbitals. It looks at molecular orbitals. Valence bond theory hybridizes the atoms and then the orbitals in the atoms and then combines them. Molecular orbital theory combines the atoms and then hybridizes all the atoms in the molecule. So we're looking at the molecule, not at individual atoms. While atomic orbitals are solutions to the Schrödinger equation, molecular orbitals are essentially guesses, or what we call trial functions, to the Schrödinger equation. The molecular orbital solutions will be checked by measuring the energy. So it's essentially the same idea as if you took an algebraic equation and instead of solving it using algebra, you just plugged in random numbers until you found something that worked. Nature will always give us the lowest possible energy configuration we can get. Nature is great at that. Anything we try to replicate based upon the complexity of an atom or a molecule is going to be naturally higher in energy, or at best equal in energy to what nature produces. So when we look at the possible solutions based on our molecular orbitals, the lowest thing that we calculate will be the best molecular orbital solution. An orbital, as we understand it, is a region of electrons around atoms in a molecule. An atomic orbital is the distribution of electrons around an atom. They are localized to a specific atom. A molecular orbital, though, is the distribution of electrons around a molecule. We call them delocalized, which means they're not stuck to a single atom. Like valence bond theory has constructive or destructive combinations where we can either build up or break down based upon our combination of the orbitals, we have the same thing in molecular orbital theory. We can either combine constructively or we can combine destructively. This occurs because electrons have wave properties, and if you're familiar with waves, waves can either add constructively and build up or destructively and break down. So looking at an example of combinations by MO theory, if we take two s orbitals and combine them together, we're going to get two possible configurations, one which is constructive and one which is destructive. The constructive combination combines the two 1s orbitals and goes from two spherical orbitals to an elliptical orbital, which has a larger region of electron density around the two atoms that are bonding. If we look at the destructive combination, they combine so that the spheres tend to disappear in the center between the two atoms, and they're on the outsides. We form what we call a node, or a dividing point, in between the two atoms. We call the first, the lower energy one, the bonding MO, and the higher energy one, the anti-bonding MO. And as always, electrons occupy the lowest energy orbitals before the higher energy orbitals. An example of this is the H2 molecule. So looking at bonding versus anti-bonding, we don't overlap atomic orbitals in MO theory, we overlap molecular orbitals. So overlap of molecular orbitals, which is constructive or additive, is going to be bonding. We call these sigma or pi. Electrons will stay more between the nuclei, and it will hold the molecule together. Now, destructive or subtractive combinations will create what we call anti-bonding orbitals. These are signified by either sigma star or pi star. Electrons cannot exist between the nuclei in these orbitals, and the nuclei will be repelled. When we look at these combinations, we can create what we call a molecular orbital diagram to represent the different energies of the molecular orbitals. And from these diagrams and the way we fill in electrons, we can calculate a bond order: single bond, double bond, triple bond. Bond order is determined from the equation whereby the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals divided by 2 gives us our bond order. So for the example, the H2 molecule, we have 2 electrons in bonding orbitals, none in antibonding orbitals. Divide that by 2, we have a bond order of 1, or a single bond. Helium, though, would have 2 in each, which gives us 0 as the numerator. Divided by 2 gives us a bond order of 0, or no bond, which creates an unstable situation. If we look at MO diagrams for these two, looking at the hydrogen combination, we have a 1s orbital with 1 electron and a 1s orbital with 1 electron, which are going to form a bonding sigma 1s molecular orbital and an antibonding sigma star 1s molecular orbital for the H2 molecule. Those 2 electrons go into the single orbital in the bonding configuration, which gives us a stable configuration, lower in energy than the starting atomic orbitals. Compare that to the helium diatomic molecule, which doesn't form. We have initially 2 electrons in each of the 1s's, which combine to form sigma 1s and sigma star 1s bonding and antibonding orbitals, each with 2 electrons, creating an unstable configuration and a molecule that does not exist. Looking at p orbitals can overlap just like s orbitals can, but they will form either sigma or pi depending upon how they overlap. The first overlap will always be sigma followed by pi. So if we look at initial overlap end on end, we combine together to form sigma overlap. So if we combine together, we have an additive or constructive combination which has a large elliptical center between the atoms and then small lobes on either side. So it has a buildup in the center and then the smaller lobes from the p orbital on either side of the atom. If we have the antibonding configuration, we have destruction in the center, so we have large lobes away from the center and small lobes inside with a node in between them. That is the sigma antibonding molecular orbital for a p combination. Now, if we compare this with a pi combination, we have overlap above and below. So our combination in a constructive way gives us an elliptical overlap above the atom and an elliptical overlap below the atoms. That forms our pi bonding molecular orbital. Now, because the p orbital itself has a node in the center already, if we combine them in a destructive or a subtractive form, like we see on the top one, we have that node in between the 2 lobes of the p orbital. Then we also have a node in between the 2 p orbitals. So we wind up getting this kind of four-leaf clover looking, or what actually kind of looks like a d orbital configuration here. And that is the pi star, or the antibonding molecular orbital. We can produce a very complicated molecular orbital energy diagram when we begin to look at all of the orbitals in a molecule. For example, the N2 molecule, looking at it, the ordering of the different orbitals within this diagram will vary depending upon the particular molecule we're looking at, because of the way that these molecules are actually combining. There is actually interaction between p orbitals and s orbitals within the molecular orbital. So what we've been representing so far has been combination of s with s and p with p. But within a particular molecule, we don't really get that. We actually really get what's more like taking the s and all 3 p's, mixing them all 4 together to make 4 orbitals. And so it's a little bit different than what we're actually representing here. This causes some molecules to have strong sp interaction and some to have weak sp interaction. This difference causes a difference in the order of the molecular orbitals. A sigma p orbital may be a little bit lower in one, maybe a little bit higher in another. It just depends upon the nature of the atom or the molecule itself, how these atoms are coming together. So if we look at a diagram for n equals 2 orbitals of an atom, like a C2 atom, or something like this, or N2 atom like the one we have above. The combinations of the orbitals for level 2, we have a combination of 2 s orbitals, and we have a combination of the 3 2p orbitals. So we can get from the 2 s orbitals a bonding sigma and an anti-bonding sigma. From the 2p orbitals, we can get a bonding pi, 2 different bonding pi orbitals. We get a bonding sigma 2p orbital. We get two anti-bonding sigma star 2p orbitals, and we get a anti-bonding sigma star 2p orbital. So we have from these 3 orbitals 3 bonding and 3 anti-bonding. So every combination of atomic orbitals will produce an antibonding and a bonding for each 2 that we combine. So the 2 s's make a bonding and an antibonding, the 3 p's make 3 bonding and 3 antibonding.